There we go. Okay, now it's recording, guys. Great. Okay. Scott Liles and Alex Hamilton. Woo! Woo!
So, nice to see you all, and thanks for giving us the opportunity to tell you a little bit about some of the things we do. So I have to apologize. I'm a bit excited about this. The last year we've been getting amazing results, and I'm as happy as a pig in smelly brown stuff. And I just get to do physics and quantum physics, and people pay me to do this. Life just doesn't get much better than that. What makes it really amazing is that not only do people pay me to do quantum physics, but industry is coming in and has found a use for quantum physics. And anyone who's trained in low temperature quantum physics, there's just a massive shortage of them because Google, IBM, Amazon, Rigetti, Dirac, SQC, any one of 20 quantum computing companies are hoovering them up. So that's really nice. It's really nice to be able to say physics is actually useful for something. So this is the group of the amazing people, and this is some of the stuff we do. We're an experimental research group. We work in condensed matter physics. And I'm going to show you two of the projects we work on, and then Scott's going to show you some of the amazing results that the qubit team has been getting with under his leadership. So we work on condensed matter physics, and in particular how electricity flows and the quantum properties of electronic devices. We've got projects on nanowires, which I won't talk about today, hydrodynamics of electrical current, artificial quantum matter, and then Scott will talk about whole spin qubits. And in terms of how people get involved with this, we've got a variety of students getting involved with the research. We've got summer projects over 6 weeks that students get involved. We've got taste of research project courses that people come and do taste of research with us. For the honours year, we have, of course, the full year research projects, and then going beyond that is the longer project. What's nice about the honours research projects, this is one of the first times you're going to get exposed to a project where no one knows what the answer is, right? So every lab you've done before, if you're doing Zeeman effect, well, come on, we know the answer to that lab, right? All you're demonstrating is that you can repeat what someone else has done. When you're doing an honours project, you're going to get to do something no one has done before, and no one knows if the answer is right or not. That's kind of exciting. So I really like that, and being able to share that physics is more than just repeating what people have done in the past. So part one. Hydrodynamics. Why are we interested in this? We fell into it by accident, but actually we're interested in it because the properties of how fluids flow is extremely universal. From the quark-gluon plasma to how blood moves through the body to the evolution of galaxies, all of this is determined by the laws of fluid flow. So, for example, have you ever thought why your heart goes? Why doesn't it just go boom, boom, boom? Surely that would be more efficient. Your heart does a double beat because hydrodynamics means there's slightly less resistance to flow. If first you fire a high pressure pulse through the arteries, slightly dilate them, and then you fire a second one. And that just reduces the hydrodynamic friction of the fluid going through the pipe and makes it more efficient. And of course, we've evolved to be as efficient as possible. So, hydrodynamics. All right, it exists everywhere. The length scale on all these are the length scales from 10 to the minus 15 meters to 10 to the 21 meters. It's not often you get to study a physical phenomenon with such a wide range of application. But what I'm going to talk about is the hydrodynamics of electrical current. So when you were at high school, probably you were taught that electricity is just like water and it flows. Is that roughly right? That was you came across that model? Okay. And of course, this is the idea of electricity, obviously put forward by the American Benjamin Franklin, who, of course, was a year later than Watson, who had done it in England, but doesn't get the credit because the Americans are always, with apologies to our head of school, are always taking credit for everyone else as well.
Unlike the Brits.
Who are just busy. Okay, moving on. Thanks, Julian. So when you get to uni, you're taught that electricity flows in solids like sort of gas particles flowing around between the atoms in a solid. And so this is Druder's model of how electricity moves. It's the electrons are these little blue balls bouncing around between the atoms in a solid, which is different than the fluid model, but not much. It's just a gas instead of a liquid. If you go to higher year physics, you actually, if you're lucky, you come across Landau-Fermi liquid theory, where we say, well, electrons interact with each other, and that interaction means that we should talk not about a non-interacting ideal gas like you did in first year, but we should talk about a liquid, because when I move one electron, because of the Coulomb force, it affects the other electrons, and that's not how an ideal gas works. So there are fluid properties of this thing, and if those interactions are strong, you really can't talk about individual electrons, right? It's like if you've got a gang of friends, you may not be able to talk about how any individual one of you would respond to a stimulus. It's what the group decides to do. You know, when you're trying to go decide where to go, it takes forever. So Landau said, well, I can renormalize all of this and I end up with an electron fluid, and the excitations of that electron fluid, if I give it a stimulus, like I give it a bit of voltage and I see how does that respond, it has an excitation of what's called a Landau quasiparticle that looks like an electron. It smells like an electron, but it's not really an electron. It's an excitation of all of the electrons together. And so there's this sort of nice picture of a quasi-horse. It's got a nose and it's got a tail, and don't worry about what's going on inside. It's still the ends look like a horse. A critical parameter for Landau-Fermi liquid theory is how long those excitations live. So in a solid, what he says is there are things that look like electrons that have a charge, but they aren't really electrons. They've got a different mass. They behave slightly differently. They're excited out of the liquid for a brief moment. They carry a bit of momentum or current for you, and then they drop down into the ground state again. How long they live for is a really good question and very difficult to know. And then, so what is this Fermi liquid, this fluid? Well, a fluid doesn't resist shear stress. It resists relative rates of deformation. So if you try and deform one part of it differently to another. And it was realized more than half a century ago, that electrons in solids would therefore have fluid behavior. The way electricity flows is not necessarily given by Ohm's law, but should also know about the fluid. And this is what I want to show you. So imagine you've got fluid going down a pipe, right? So this would be, say, a piece of wire, and this is an electron moving through that wire. And it bounces off either the edges of the wire or it bounces off impurities inside the wire. So it bounces around, and there's a voltage pushing it from left to right. If the distance between these collisions is small, the mean free path, then it moves diffusively. So this would essentially be almost like Brownian motion, and then you put a voltage on it and it drifts across. So the resistance of this bit of wire is set not by the properties of the electron, but is set by how far apart these collisions are, phonons, impurities, and so on. It's not an intrinsic property of the electron fluid. If you make the wire really, really clean to study the electron fluid, then the resistance of the wire is only set by, well, the electrons move, it's so clean, they move through the wire, and then they hit the side of the wire, then they bounce off, they hit the other side of the wire, they hit the other side of the wire. The resistance now is set by the sample geometry and the width of the wire. Again, it doesn't depend on the electron fluid or the electrons, right? Because they just move without hitting anything. If you include electrons bumping into each other, then there are lots of collisions where the electrons are bumping into each other, just like a gas. And now the resistance of this wire is set by the viscosity as well as the sample shape and size. And the viscosity is how often the electrons bump into each other, which is this quasi-particle lifetime that Landau was talking about. So all you'd have to do is measure the resistance of wire, and you can measure the properties of the fluid. You've just got to find a material that's quite pure and that's got a lot of electron-electron scattering. So that's simple, and everyone thought that should be simple, but it turns out to be really hard. And that's because when a fluid flows through a pipe, the friction to that flow is set by how smooth the sidewalls of the pipe are. If you've got a perfectly smooth pipe, then fluid can flow through it without any friction. There's no way to dissipate energy. So if I asked you to try and make water flow through a perfectly smooth pipe, or honey to flow through a perfectly smooth pipe, which is harder?
Honey.
They're the same. There's no way to dissipate energy, so there's no resistance to the motive force that you're applying. So the viscosity of the liquid doesn't affect the momentum flow, right? It just redistributes momentum. So learning about the liquid in a perfectly smooth pipe doesn't work. Well, you say, I'll just make the edges rough. And so there's this idea that if the edges are rough, then you get friction at the edges, and that will tell you about the fluid. The problem is, what is it that determines how rough the edge of a pipe is? Is it the width of the corrugations, or is it at the atomic scale? What do we mean by roughness? And as an engineer, it's a parameter that you don't know what it is. You fit the data and you add it in at the end. And as a physicist, you go, yeah, I don't like that. It's an unknown parameter. So there've been a series of experiments culminating in people actually seeing electricity flowing through a pipe. They put two lobes on the side of the pipe, and they saw as the electricity went up here, you've got little vortices, little whirlpools going each way, and they imaged that with a scanning squid. This is very nice, but really, really difficult to do. A scanning superconducting quantum interference device attached at the bottom of dilution refrigerator. There's about 2 of them in the world, and only about 0.5 people in the world who know how to use it properly. So we don't want to do that. So we want to think of another way of doing it. So the problem is, A, these are hard experiments to do, and B, it still depends on what you see depends on how smooth these walls are, how well that vortex forms. And really, I don't want to have a parameter that I don't know what's going on. So one of the things we've been having a lot of fun with is introducing hydrodynamics without having to use the boundaries to create that viscous dissipation. So well, how can you do that? It always depends on the walls of the pipe. No, electrons are different than water. They have charge. If I have an electron moving in a magnetic field, what happens? Lorentz force, it bends. So if I have a magnetic field that's first positive, then negative, then positive, then negative, as the electron goes through, first it bends to the left, then it bends to the right, then it bends to the left. So it sort of wiggles as it goes down. If I've got a lot of electrons and I try and make them wiggle, it makes them bump into each other. And that is what causes a lot of, it's like I'm stirring the liquid, like you stir tea. And so I'm alternately stirring it one way, then stirring it the other way, then stirring it one way, then stirring it the other way. And so that alternate stirring causes energy loss. And so I can measure directly the viscosity in a pipe that's infinitely wide. I don't have to worry about the boundaries at all. And I can create an enormous signal. And well, we've been having, some of the undergraduate students have been having a lot of fun doing this. We've got a new idea based on anyone who drives in from the north side of Sydney will come across this on a regular basis. And this is another example of fluid dynamics. Traffic is a fluid. It's a fluid of annoyed drivers going, no, you go first. No, you go first. No, you go first. And there are car-car interactions. Sometimes they're a bit direct, which is not ideal. But even indirect long-range interactions, just like the Coulomb interaction, causes vorticity and causes the equations that describe how traffic moves when you've got a large number of lanes going into a small number of lanes. That is fluid dynamics. And so you can design transistors that work completely differently to the transistors we use today that work on fluid dynamics properties. So that would be really fun. And where we've got to so far with this is we've had some of the undergraduate students doing experiments, and Callum, Priya and Pav are all undergraduate students, and this is their paper that's just gone on the archive this week reporting their work. So that was not bad for summer projects. So one of the projects we've got is to continue these experiments and start looking at what we call traffic jam transistors. So if you feel that you're spending too long on the bus waiting to come in, come and do this sort of stuff. The timescale for the traffic jams that we're talking about is picoseconds, not hours. So, okay, so that's hydrodynamics. What materials we do it in? We do it in advanced semiconductor materials. You could also do it in this material, which will be fun, which is related to the work we did in Fleet. This is a material invented by these two crazy Russians who won the Nobel Prize. They also won the Ig Nobel Prize, or one of them did, for graphene. And the really cool thing about this material is you don't have to use super expensive crystal growth platforms. The way you make this, you can make a single sheet of graphene, 1 atom thick. And the way you make it is you take a piece of graphite from your pencil, scrape a bit of pencil off. That's how your pencil works. It's held together within the layer by strong covalent bonds. The layers are held together by weak van der Waals bonds. So you put it on a piece of sticky tape, you fold the sticky tape in half, and then you unfold the sticky tape. Now I've got 2 pieces of graphite, each half as thick as the original starting piece. So if I started with something that was maybe 0.5 millimeter thick, and I fold it and unfold it, now it's 1/4 millimeter thick. And then I fold it this way and unfold it. Now I've got 4 pieces that are 0.1 millimeters thick, right? And you can keep doing that folding. How many times do you have to fold it before it's 1 atom thick? Yeah, it's about 20 times. The power of exponentials. If we learned nothing from COVID other than exponentials, you just keep folding this thing and you end up with 1 atom thick, and you can make transistors out of that, right? 1 atom thick transistors. And you can use, and so we've been doing that, and we've got undergraduate students doing that. And then you don't just have to keep putting the same material on top of each other. You could use 1 bit of sticky tape with, say, graphite on it, 1 bit of sticky tape with hexagonal boron nitride, and you can just stick them on top of each other with bits of sticky tape, and you can play atomic Lego and make artificial structures, literally building stacks up 1 atom at a time. I mean, it is a bit annoying, but you can do it. And the nice thing is the cost of doing this is tens of dollars. The cost of doing it in a crystal growth machine is tens of millions of dollars. So a lot more people are doing that. Okay. Second project is synthetic quantum matter. Why we're interested in that is 2. 1, wouldn't it be fun to make any quantum matter that you wanted, not just say carbon or silicon or whatever, but a completely new kind of matter. The other is that if there are certain classes of problems that are really difficult to solve, and it would be nice to actually use nature to solve them itself. So you could build, if you can map a problem onto a Hamiltonian and then build a system that automatically solves that Hamiltonian. There's kind of a lot of work on doing quantum simulation. So what we're doing is saying, okay, what makes a solid a metal or an insulator or a magnet or a superconductor? Well, what I know for sure, it is solids are made of atoms, and the properties of solids are determined only by how you arrange those atoms. That's all that differs. What are the atoms? How do I arrange them? Once I specify that, I fully specify the solid. So you could, if I say to you as a theorist, can you make this? That's a very different statement than if an experimentalist, can I make an arbitrary solid? Because nature says, well, the bond lengths are this big, and these things react with this, and so you can make those compounds, but you can't make other compounds. So there's a limit to what we can make. Wouldn't it be nice if we didn't have that limit? If we could make any material we wanted? How about, okay, so the properties of materials are set by how far apart the atoms are and how many electrons the atoms have. So what we do is we make arrays of artificial atoms. We can put them in any geometry we want, and then we can change the amount of charge on each of those artificial atoms. And we've got a gate stack for doing that. We use semiconductor nanofabrication technology to do that. That's perfectly possible. You could also use the sticky tape technique to do that. And so what we're doing is we're creating a periodic array of atoms and separated by a periodic array of barriers. And because we've got different electrodes, we can control the period, that's set by the nanofabrication. We can control the number of atoms on each, electrons on each site, and then we can control the potential barrier between those. So if you've done when you do solid state, you've done solid state physics, right? Some of you have done that. You will recognize, oh, that's how we derive band structure. So now what we're saying is you can design any array of atoms you want. You can make any crystal you want. You can change the number of electrons on each of these sites to any number you want. So you can make matter with any electronic, magnetic, superconducting properties you want. All we've got to do, we're getting very good at making these. Now we've just got to measure them all. So there's projects related to that. So I think I stopped there. And those are the two projects I want to talk about, and I'm going to hand over to Scott. It doesn't, I lost the bit.
Let's change that. Cool.
Yeah.
Okay, thanks, Alex. And also thanks everyone for being here, and thanks to Physoc for organizing this. I'm a postdoc in Alex Hamilton's group. I do research here in the School of Physics, and I'm going to talk a little bit about the work I do on whole spin qubits. The outline is I'm going to go over the general motivation for doing this research. I'm going to talk a bit about electron spin qubits, and then I'll talk about the really cool thing, the whole spin qubits. But before I get into all that, just a little question. If you have heard about holes before, you will know that in solid state physics, this is how we describe a missing electron. You can think of a hole in the same way you might think of a bubble in beer. The bubble is easier to describe the motion of than the beer which is moving around it. And the thing that I'm going to be talking about, which is my research, is actually using holes to do quantum computing. And so a question is, how can that be possible? How could someone use the absence of an electron, just empty space, to store information? And hopefully by the end of the talk, you will agree with me that it is actually fine. So I'm an experimental physicist. I work in condensed matter physics. I do solid state condensed matter physics. And my motivation for my research is the field of quantum computing. I really like this field because I get to stay in touch with concepts of solid state physics and quantum mechanics, amongst obviously a bunch of others. I also, by doing experiments, I get a bunch of hands-on experience. I've experience with semiconductor processing, which is a valuable skill if you want to move into industry. This is a trillion-dollar industry. The experiments that we do, you need to design complicated circuits to control qubits. So I have to keep on top of some electrical engineering aspects. And then another big aspect of my job is dealing with cryogenics. We regularly use liquid nitrogen, liquid helium to cool samples to 4 Kelvin. And then these guys, this is the inside of a dilution refrigerator, which we use to cool our samples to 10 millikelvins. That's 0.01 degrees above absolute zero. So they're pretty fun to work with, very interesting. And then the other reason that this field is great is because there is a global push right now to develop quantum technology. All around the world, different companies are putting a lot of money into developing quantum tech. As Alex said, they're going to need the workforce that has a background in quantum physics and has the experience to work with these hands-on tools. Also, I can see you on there. That's fine. Boo, no. Also, Australia has a really, has put a priority into this quantum tech. So there's a lot of startups, there's a lot of research focus in Australia, actually in Sydney, that's focusing on this physics and these industry problems. I'm a physicist, so my job is not to engineer a quantum computer. My job is to study the physics that would be used to solve problems associated with quantum computing. Before I get too deep, just very quickly, what is a quantum computer? Most people recognize that a regular computer uses binary bits, so ones or zeros, to store and process information. A quantum computer is a type of computer that doesn't use binary bits, but instead uses quantum bits. We call these qubits. And what a qubit really is any sort of two-level quantum system. So a system that has two quantum states. It could be the spin of an electron up or down. It could be the polarization of a photon. Any two-level quantum system that I can write like this, you can use as a qubit. And the sort of idea is that you can create, you've probably heard this before, it's the tagline. Instead of your qubit being in a 1 or 0, you can have it in a superposition of 1 and 0. And then the other cool thing is you can, once you have multiple qubits, you can actually entangle them, and this gives you access to a whole bunch of new algorithms. And this is part of the reason why there's a global challenge to actually build or engineer the best qubit and use it to design a quantum computer. All right, so the actual physics stuff. UNSW is probably safe to say world leader in silicon qubits. There is so much expertise here at UNSW in silicon qubits. And this is what I research as well. What we do with these silicon spin qubits that I'm going to talk about is use the spin of an electron or a hole as my qubit. As a quick backup, maybe you didn't do quantum mechanics yet. So what is spin? If you know what spin is, you can like tune out for 5 seconds because this may upset you. But if you don't know what spin is, a simple way to think of it is an electron. Imagine it's a particle. Imagine that you could have this particle either spinning clockwise or spinning anti-clockwise. It's not the right way to do it, but it sort of works as an analogy. And we can call the one that's spinning clockwise spin down, spinning anti-clockwise spin up. And then we can use these up and down 2 levels as our 2-level quantum system for our qubit. So that's the concept. The really interesting thing is how do you actually get an electron in a situation where you can rotate its spin and use that to store information? And the way we do that is with these very advanced metal oxide semiconductor materials. We use silicon. Silicon's a great material for this because it's a semiconductor. This means that unlike a conductor, which just has so many electrons that you can't ever get rid of them, or an insulator, which just has no electrons, you can design a semiconductor such as silicon so that you have just a few electrons. Then we cool this silicon to really, really low temperatures so that thermal vibrations aren't going to wreck our system. And then if we apply a positive voltage to a little piece of metal here, the electrons that are wandering around the silicon will eventually get pulled up and attracted towards the positive charge. They get blocked by this oxide. And here we have a single electron trapped in what we call a quantum dot. Now that we have the electron trapped, if we apply a magnetic field, it'll split the energy levels by what's called the Zeeman energy. And then we can do experiments where we apply photons at the resonant frequency, and depending on how long we apply these photons for, we can drive coherent oscillations. This is how we would control an electron spin qubit. So that's great. That's really cool. The thing I work with is actually holes. So that's what I want to get into. And so first of all, I should explain what is a hole. So in silicon, I mentioned we can control the number of electrons. Not too hard to imagine one electron and then go to several. Okay, I can add some more. And at some point, I will have filled my silicon up with as many electrons as I can fit in my silicon. So basically, I've put in as many electrons as I can get. And then what I do is I just pluck one out. And this leaves behind an electron hole, the absence of an electron. And just like I mentioned at the start, it's going to be much easier to describe the motion of this system by just thinking about how this hole moves around rather than thinking about how all the thousands of electrons are actually moving out of the way of the space. So in that sense, we think of this hole as like a bubble in this electron sea. We can call it a quasi-particle. It's not a real particle after all. There's nothing there. It's empty space, but it's easier to just describe. Okay, so that's the concept of a hole. It's our missing space. And so if you've never come across this before, maybe it's still confusing as to how you could actually use empty space to do quantum computing. And so this slide, I want to try to convince you with some very simple thought experiment that an empty space can actually have a charge and can actually be spinning. So what do I mean by that? Let's play the game. Let's imagine that someone has collected 8 electrons. Each electron has a charge of -e. So the total charge of this system is -8e. Each electron I've given spin down or spin up, and they all are sort of paired up. So the net spin of these 8 electrons is 0. Like mind-blowing, everyone's done. Okay, so now we add in the hole. Maybe this doesn't seem like this seems like a trick maybe to say 8, I'm going to have 8 electrons and 1 hole. But mathematically, this is actually the valid way to deal with this system. I had 8 electrons, and then I kicked one out, which means I added a hole. So this system is 8 electrons and 1 hole. Now, if I look at this system, since there's only 7 electrons there, I can count up the total charge, and I can say the total charge here is -7e, and that has to be equal to the charge of the 8 electrons plus the charge of the hole. And if you follow the math through, what you end up getting is the hole, which is empty space, nothing there, actually has a positive charge. And by the same maths, it's maybe a little simpler. The net spin of this system is actually there's 4 ups and 3 downs. So we get plus S. Therefore, this hole actually also has a positive spin. So this is empty space is carrying some quantum angular momentum. If that's really bugging you, it's like a maths game. If it's really bugging you, you can just think of this example. Take our 7 electrons and our empty space, put it in an electric field. What's really going to happen is these electrons are going to want to get to the positive charge. And that's what happens. One by one, they shuttle across. But you can also see that our hole is one by one shuttling towards a negative electric field, acting just like it has a positive charge. So that's what I really want to emphasize. The hole, don't think of it as empty. It's actually a particle here. It's carrying charge, and more importantly, for me, is carrying spin. So we can actually play more or less the same game now. We take our silicon, we fill it with electrons, and then kick one away. And then, there we go. And then as the hole moves around, we put a negative voltage on this piece of metal. Of course, in reality, it's pushing the electrons away. But if we're thinking of hole world, we've attracted and trapped our hole just below our gate. We have the same situation now, a hole trapped in a quantum dot. The hole has a spin, and so if I apply photons at the resonant frequency, I can drive coherent oscillations. Great, so this is all like fun little pictures that I had some fun making over the last couple of days. What you really care about is this even physically possible? Or at least that's what I care about, and that's been a key feature of my research. And I'm going to show you, spoilers, yes it is. So this is a more realistic version of a device that we studied. This experiments were done by a PhD student in our group, Isaac. This device has 2 little spots where we can trap 2 different holes. And what Isaac was able to show is that here on the y-axis, we have the probability of this hole being in the spin-up state. And the x-axis is how long we apply a control tone for, how long we put these photons in. And we see really nice, rapid oscillations of this spin from up to down. We can also control the second spin. So this one's a little easier to look at. So you can see as we vary the time that we burst it for, the hole that we apply the tone for, the hole goes from spin up to spin down to spin up. And then also really cool, if we stop just here, we've actually created the superposition that we need. The hole is 50% up, 50% down. And so what we have is a 2-spin qubit system, which we can use for our whole spin quantum computer. Okay, so I think that's really cool because just to emphasize, we are flipping the spin of a missing electron and then measuring that. But if you're kind of pragmatic, you might say, like, you had an electron spin qubit, who cares? Like, you've got a whole spin qubit, that doesn't really impress me. And if you say that, I would say, that's kind of rude. But also, I didn't tell you why we would care about whole spin qubits. So I will give you the selling point. The thing is that holes are not exactly the same as a positive electron. And the reason for that is the properties of the hole depend on the properties of the electron that went missing. If you've done some solid state physics, this will look familiar. This is the band structure of silicon. And if you haven't done it, I'll try and also make this understandable, but the electron spin qubit is using electrons that occupy this, which is known as the conduction band, whereas the holes are missing valence band electrons. And the conduction band and the valence band are made up of from different atomic orbitals. Short version is they have very different properties. And so the spin qubits based on electrons are expected to have very different properties to spin qubits based on holes. And that sentence there is essentially the motivation for all my research, is to study the spin qubit, study the physics of whole spin qubits. I found they're really confusing and complex. This is like an info dump of all a bunch of the papers that have come out of whole spin research here at UNSW. It's not all of them, it's just the ones that I've read and could fit on this graph. But the thing I want to point out is there's still plenty to do here. We're still pushing this forward. I've been in this field, like this was my paper. This is my first paper, actually. I've been here since 2018, and there's still new interesting whole spin physics to do. So if you want to come and study the physics of holes, you're welcome to come and join us. As Alex said, if you want to get more info, you can contact me or Alex. We have opportunities across undergrad, honors, and PhD. And just as a fun example, this is Dan Halverson. He's an honors student now. He did a summer project and then I believe a taste of research with us. And that research ended up getting him a second authorship on a paper we recently published. So yes, that's everything I have about holes. Thanks for listening. And sure, yeah, questions.
What's the process of creating a hole?
The process of creating a hole, that's a great question. If I say Fermi energy, do you know what I'm talking about?
No.
Okay. Basically, silicon naturally, like silicon out of the box, has the valence band completely filled and the conduction band completely empty. And so if you, basically the way we think of that is there's an energy level which is sitting right here, approximately 0. And then it's up to you. If you apply some, if you want electrons, you apply a positive voltage and you start adding electrons to this conduction band. If you want holes, you do the reverse and you start kicking electrons out of the valence band. So it's to do with the voltages that you apply in your silicon. And you can also do some tricks with doping. There's a lot, yeah.
Yes. What happens if you forget the number of electrons you started with?
Oh, that's a really good question. I didn't include it in this device. Okay, that's a very complicated question. I'm going to give a simple answer. We didn't include it in this device, but we actually have right nearby a little sensor which counts how many, in our case, how many holes we have in our dot here. And we can actually count them all the way down to 0. Yeah, there's more technical aspects to that question, but we build in a little sensor, really sensitive electrometer, and we can see the holes like coming in or disappearing. So we count them up. Cool. Thanks, everyone.
Yes, yeah, it's very similar. Almost identical. The easiest thing is to manage. Yeah, that's all. That's not necessary. It's so
Okay, guys, we're back. There's going to talk about the astro assessment evolution. Just in terms of questions, since we're on a bit of a time crunch, feel free to ask questions in our little interlude session we had before. Well, I think their emails will be displayed up there. So yeah, we'll just do questions at like the interlude area, just so we're aware of time. Well, thank you.
Right. Now, before I start, who knows what astroseismology is about? What is that? One person. Okay, good. So, excellent. Go forward.
Oh no, you have to do the like the arrow.
Okay. So, I thought so. So, I have a short introduction, a crash course into astroseismology. And I will start with the HI diagram. Some of you have seen it, some of you might have not. It's basically the periodic table for astronomers. It shows luminosity of stars and surface temperature. So they are both for surface properties of stars. And we can already see there are trends there, so we can learn something about stellar evolution in this diagram. The problem with surface properties is that they don't probe their interior. And astroseismology does. It's the only way we can really see inside stars. Now, most of the stars in the sky are these kind of yellow and red stars, and they have something in common, and that is that they have surface convection like the sun. So it's basically turbulent motion at the other part of the star. And in the sun, we can see it, because if we take a picture, we can see the granulation pattern of this hot gas coming up and cooler gas going back down. Now, it doesn't look like a movie when you look at it, because it takes several minutes for it to change, because the sun is pretty big, and these granules, as you can see, are pretty big too. But if you want to see it real time, how this sort of granulation pattern looks like, you just go to a Japanese restaurant and order miso soup. Because there, the same thing happens, but on a time scale of seconds. You can see it, but it's exactly the same physics. So in the star, this sort of turbulent motion hits the star surface from the inside, and that excites standing waves, just like sand grains in a gong. So you have this big ringing bell in the sky, which is the sun and all the other stars that are similar to it. So that's how they ring, and they can ring in all these different ways. So this is their actual vibrations, and they are spherical harmonics. You might know them from quantum mechanics, and this is how they look like. So we can actually measure. We can obviously not hear the sound because there's empty space between us and the star. But we can actually measure the vibration, and we can do it either by effect, by measuring how the light gets slightly red or blue shifted as the star is moving towards us and away from us as it rings. But that expansion and contraction of the gas also cools and heats the gas, so we also get a variation in brightness, so we can measure the brightness variation as well. And so we can measure the vibration and therefore the frequencies of the sound waves in the star without hearing it. And those frequencies are obviously the same as the sound waves inside. Just to give you a sort of scale of this, the velocity for the sun for these vibrations are like walking speed. And the variation in brightness causing by this is sort of a fraction of a degree on top of this 6,000 degree surface that the sun has. And so it's tiny, but we can do it. And the thing is, so this is the crux of what astroseismology is. We measure frequencies from these vibrations, and these are the frequencies of standing sound waves. So we basically get to know the sound speed, as you would know from first year physics. And you also know from first year physics that sound speed depends on the interior properties, so the properties of the medium. And so that's what we do. So this is an experiment that was very good at it, called Kepler. Who knows the Kepler mission? Yeah, quite a few. So basically a 1 meter telescope. It looked at one patch of sky for 4 years. It has this huge CCD because it had a lot of stars to look at. This is what it looks at, one field. It's the total field from Kepler. If we zoom in on one CCD, we can see there's lots and lots of stars there. So what Kepler did was very simple. It just measured how much light fell on the CCD every half hour. And so for a given star, you could therefore build up a light curve where you have a data point every half hour for 4 years. And it did that for hundreds of thousands of stars. And it was obviously built to do this, which was to detect stars that have planets around them that would block some of the light. But for us, that was pretty annoying, those transits, because what the real signal is of course, this variation that we have on top that you see here. So if we remove this annoying transit, you can see the interesting signal here. And that's the oscillations. So that's the brightness variation caused by the vibration of the star because we have standing sound waves inside. Now, in reality, we don't look at the light curve because it looks so complicated. As you can see in the example here by the sun, we take Fourier transform of it, and then we look at it. Because in the Fourier transform, it looks beautiful. You see this broad hump of power where we have a lot of power sticking out above the noise. And each peak here is an oscillation that occurs in the star. So it's an oscillation mode of that particular frequency. And we can see it has a certain pattern to it. If we zoom in, it has this characteristic pattern, and I have some numbers on them. They just indicate what sort of oscillations they are. There can be radial modes, or there can be non-radial modes of different forms and shapes. And so we can recognize that, and we can therefore learn about the star because we get all these frequencies. Now, what can we extract from all this? One thing is obviously size, because size really matters when it comes to the sound you produce, as is quite evident when you go to the symphony and you listen to these things. You can pick up by close eyes where the bass is and where the violins are. Example here from stars again. This is Kepler data from 4 stars. You can see they go up in brightness, up and down, roughly the same number of times, all 4 stars. The top one takes 20 days to do it, where this one does it in only 2 days. So what do we know about their relative size? Those 4, just by looking at this plot. They go bright and dim the equal number of times, but the top one takes 10 times as long as the bottom one. Yeah? What's the difference? Top one is bigger, a lot bigger. And in fact, these were the relative sizes that we got from this data relative to the sun. These are all giant stars. Okay, but we can do more than that. We can measure surface gravity and surface temperature from where this characteristic hump sits. We can also measure density, but what is very interesting is we can measure the ages of the stars, and that is extremely hard to measure any other way. So ages of stars is basically the big problem in stellar astrophysics. The way it works is that some of the modes or the waves, they travel straight through the star, the radial modes here, and that means that part of their journey goes through the core where hydrogen turns into helium. And just like when I inhale helium, I start to sound like Mickey Mouse. This mode will start to sound more and more like Mickey Mouse as more helium gets into the core as it gets older and older, whereas the modes that don't go into the core, they won't feel that difference at all when the star gets older, which means that the frequency difference between these 2 modes become a measure how much helium has accumulated in the core and therefore its age. Okay, but we can do more than that. And I won't go too much into detail because there's lots of information here, but just back to our periodic table here, it was useful for hundreds of years, or at least over 100 years, to figure out what stars were doing when they were evolving. But for certain evolutionary phases, stars occupy the same region here, basically meaning we couldn't tell apart stars that had the same luminosity and same temperature, even though they were actually at different evolutionary phases. So there was only different in 4 properties, and the seismology can tell that apart. So here we have 2 very different stars. they're in different evolutionary phases, and we can see there are clear differences for some of the modes. Here they are separated by a lot, and here they are not. And that is because one of them is burning helium in the core and the other one is not. But we can do more than that. We can also measure internal rotation. And just like Siemens splitting in an atom or an electron, we can have lifted degeneracy, and therefore rather than having one peak from a mode, we suddenly get three because of this shifting of rotation. And we can see we get a triplet structure every time we would normally find one peak. And how much they split basically tells how fast the star is rotating and where that mode is really spending most of its time. And you can see the modes, and I can point that out. These modes spend more time deeper in the star than these modes here. So you can see that deeper in the star, there's more splitting. It rotates faster than closer to the surface. And it turns out when we measure the rotation from this, it doesn't match the theory at all. So we have not yet, but we certainly know that we don't know anything about how angular momentum transports inside stars. This is just fundamental physics we can't grasp by an order of magnitude. Okay, the final thing I wanted to highlight is magnetic fields. Magnetic fields we can measure at the surface of stars, but not in the cores, except when we use seismology. So up here we have again Fourier transforms of some normal stars, and I have some different stars that are otherwise identical. We can't tell the difference other than in the seismology. We can see some of the modes don't have power there, the red ones. And that is because there's a magnetic field in the core. So we can learn something about how magnetic fields and dynamos work in stars when we have charged particles that move around in the core of stars. And that is something we otherwise would have not access to. Okay, so that was my crash course in astroseismology. So now you're experts. And this is what you should therefore should care. We went from quite recently from this sort of field where we had a handful of stars where we could play this game to suddenly have thousands and many thousand stars in our periodic table here. And this is actually an old plot, as you can see. Kepler's ended its life in 2013. We now have the test mission, which looks through the entire sky, and you can add another 0 here. So we have hundreds of thousands of stars where we can do it. That means that we can now learn a lot about the Milky Way, rather than just our near neighborhood here around the sun. We can really start to have information about where are the stars and what are their ages. And we can learn about the evolution of the galaxy by having age probes from the stars in the galaxy. And so that's what we call galactic archaeology, and astroseismology has done a lot in this field and is still doing that from all these measurements. This is the test mission I talked about. It looks through the entire, or the whole sky, and that is why we have these huge numbers of stars from that mission. Now, what we are working on, particularly at UNSW, is to kind of remove the bottleneck of the analysis. As you can see, we have plenty of data. There's no doubt that, but we don't have so many people. And therefore, we want to speed up the process. And so we have worked a lot on using various AI methods, so a lot of deep convolutional neural networks to do some of the aspects of the analysis that it can do really well to speed us up. And we have had lots of success with that. And so the way it really works is that these convolutional neural networks can really see the sort of features that an expert would look at. And it will highlight the same things that an expert would highlight to make its decision. And that is why it works so well. Okay. But what is coming up? We have a European mission, Plato, and we have a NASA mission, Roman, coming up both in 2026. So that is even more data. And Roman is particularly interesting. It looks straight into the center of the galaxy, where we have no detailed information about the stars so far. So that will be quite revolutionary. So with this kind of short introduction, I hope you can see we have plenty to play with. And if you think you'll be interested to work on some of this, just send me an email. We have plenty to work with, not so many people. So it is a free smorgasbord. So that's it.
Okay, thank you. Me again. Do you want to use the whiteboard? What are you saying?
Oh, see how we go.
Okay, yeah, sure.
Make it up as I go.
Yeah, of course, I think I can probably sort out that table, but yeah, I think so. Where the
You don't even worry about technology, right?
yeah.
Work out with it.
Yeah, we'll push. I think, I don't know if that room has like a movable microwave. But like,
It's fine. So simple. It's like, don't worry about it. Don't stress
you
it.
sure?
Yeah.
Okay.
All right. So, hi everyone. Sorry. So like I just got off a plane like a few days ago, and I'm jet lagged, and I didn't make slides because I thought crap slides are worse than no slides. All right. So I'm Julian Berengut. I'm an atomic physicist, and atomic physics is for when atoms are hanging out by themselves. So not in a solid, not in a star, but hanging out by themselves. Where would you find atoms hanging out by themselves? An ideal gas. Sure, particular ones. Only noble gases. Where else? Space. Yep. Where else? There's good ideas. So I wrote space. But also plasma, also cold atoms that we do in the lab. I mean, if you really wanted to make, solid state devices that are built to specification, you do that using ultra cold atoms, and it's fewer elements, but very carefully arranged. And the other places that you would see is a sensitive atomic clock, of course, which is important. The atomic clocks, of course, define the fundamental constants of nature and also measure those fundamental constants of nature. So basically, atoms are at the source of physical, what we call metrology, how we measure things. So I'm going to give you a couple of examples of what I do with atoms. And for me, the periodic table of atoms is the periodic table of atoms. And so and then I'm going to quickly explain why what I do is hard, because I'm a theoretical atomic physicist. And you might be wondering, surely we did theory for atoms like 100 years ago. Why are you still here, mate? And that's a reasonable question to ask. And I'll give you a pretty reasonable answer. So bear with me. Ask any questions as I go along, please. I made a list of notes here. I'm not just winging it. Hey, so fundamental physics. This is the first thing. You got the standard model of particle physics, and I'm sure that Mikhail Schmidt will talk to you after the break about the standard model and particle physics. And there are different ways of looking for physics beyond the standard model. And one of them that you would have heard about is the Large Hadron Collider, where you smash things together and see what comes out. What are we looking for when we do that is new particles. What are we trying to find? We're trying to find things like dark matter. You all know that like dark matter, there's more dark matter than there is ordinary matter by weight in the universe. Here's the thing. Do you know about missing matter? So we did the cosmologists, they're smart. They come up with the idea that like the universe is 70% dark energy, 25, I'm making up these numbers, 30%, 25%, 25% dark matter or baryonic matter or dark matter, not dark energy, and then 5%, 4%, 5% is like ordinary matter. And so then the astronomers go and look at the sky, and they were like, well, I can only see 1% of that matter. Where's the other? So 80% of that thing that we call visible matter was missing from the universe. Do you know where it is? They found it when they went up there with the X-ray telescopes. It was behind the dark matter. No, of course it's not behind the dark. That's just embarrassing. No, it was in the form of plasma. It's in the form of plasma. So astronomers were looking at optical and highly charged ions that have like atoms that have had electrons moved, radiating at a different frequency that you can't see with ground-based telescopes. Okay, so plasmas are important.
You got me so hard. Oh, this is embarrassing.
That's how it works, mate. Okay, so you're looking for you're looking for physics beyond the standard model, and why are you using atoms? So you're looking for dark matter. There's the kind of dark matter that you've been looking for with your Large Hadron Collider is the heavy one, something that is like a particle that exists but only at high mass. And then you think, well, we haven't found anything. What else can we find in our bag of theories? And you might find light dark matter, light dark matter like scalar fields, very light, ultralight dark matter like axion. And so what you can do is look for ultralight dark matter, ultra low mass, that means low mass dark matter, using very precise measurements. How precise are we talking about? In astronomy, we look at we try and trace atoms, atomic spectra as a function of gravity, and that we can get at sort of the 10 to the minus 8 level. So that's almost 10 parts per billion, which is pretty incredible, high precision. And so this is an extremely sensitive test in astronomy. On Earth, we've got atomic clocks, and the atomic clocks, we can measure that at 10 to the minus 18 relative precision. So 1 part per billion per billion. That is the most precise measurement in all of physics and, of course, all of science, by a lot.
What were those pulsar things?
Sorry?
What were those pulsar things?
That's that question.
The spinning pulsars in space.
Spinning pulsars have a very, very high repetition rate, but they also have some glitches and things like that. We're talking about that's also very, very accurate. But there's nothing quite like an atomic clock. What's great about pulsars is they have a very long baseline. Why would you look at atoms to find dark matter? What's dark matter doing to an atom that you can look for? Well, what happens is this ultralight dark matter is actually in the form of a Bose-Einstein condensate because there are many, many particles per unit of phase space. And so it's a Bose-Einstein condensate, and it's like all moving as one with a single wave function. This is the dark matter. And you've got an atom sitting somewhere inside that. And the way, if there's any interaction between the dark matter and the light matter, which we expect that there should be because somehow that dark matter had to form from the Big Bang, that's another story, we won't talk about that, then it will change the fundamental constants that we perceive in the atom itself. So what we can do is look for, is the speed of light what we expect it to be? If it is, then we say, okay, that's like that we don't have any evidence for dark matter. But if we do see some variation, we may say, okay, we found hints that dark matter exists. And there's reasons that ultralight dark matter is good for axions and so on, but I'm not going to go into that either. I think we can do search for new particles. I'm not going to talk about that either, but I've been doing it for a long time. Yep, skip. All right. Moving right along. So complementing LHC, I think I've told you enough about that. The other thing that we do with that is, of course, what's at the bottom of the atom is a nucleus. And our atomic physics is now so precise that we are doing extremely sensitive nuclear physics with atoms. When you think about what a nucleus is and who's hanging out with it, the electrons have a wave function which penetrates deep into the nucleus. Now that is good because it means that we could do nuclear physics. It's really bad when you're trying to find new particles because nuclear physics is really hard and we don't know what a lot of stuff is in the nucleus. Nuclear physics is really, really tough. But the electron that's in the atom gives us a way of probing the nuclear physics. Why do I want to do that? We've got, have you seen the nuclear chart in the third year lab perhaps? There's like proton number versus neutron number or vice versa. And you get this like, this is the stable guy. Yeah, that's right, that line of stability. And that line of stability is essentially the experiments that you can do on Earth. It's like the 100 or so elements plus their isotopes. So you've got, I don't know, like a few thousand in total. And then you think, okay, is that all of the nuclei that there are in the world? Almost. If you then go another like 30 orders of magnitude in that direction, you get to neutron stars. And we want to know how neutron stars work. And so what we're trying to do is extrapolate from this thing out 30 orders of magnitude in that direction. Okay, that's not easy. And that is a chief goal of nuclear physics. And what we can do with our atomic physics is tell you what happens when you add neutrons to atoms. And actually, we can get really close to what's called the neutron drip line. And then we can be learning stuff about how neutrons interact at that scale. That gets complicated. Next topic, plasma physics. We've heard about quantum computers today. You haven't got any though, have you? No one does. What you've got instead is actual computers, and I've got one right here. Actual computers are currently made using nanolithography. Really, really complicated stuff. You basically shine light on a silicon substrate. There's a resist there, a photoresist. It's like old school photography. It's like nanolithography. And one of the key problems with that is making the light smaller and smaller, because the smaller you make the light in terms of wavelength, right? Higher power light at high frequency will give you a smaller transistor at the end. So what we're trying to do is you go, optical to the UV to the deep UV, and now we're at extreme ultraviolet light. That extreme ultraviolet light is at 13.5 nanometers, and it is created in the most insane process you've ever heard. It's created by taking a droplet of tin, the metal. You whack it with a laser, bam. You whack it with another laser, bam. And then you're basically producing 13.5 nanometer light in the extreme ultraviolet. That light is then reflected 10 times by multiple layer mirrors, and then it's projected onto a thing. Okay, cool, whatever. So inside this thing, you've got all these tin atoms that are making these 13.5 nanometer light. How does it do that? Well, these are highly charged tin ions, tin 10 plus, 11 plus, 12 plus, 13 plus. There is, if I tell you about the single part, I'm not going to go into the details. Tell you about the single particle model, and you do some like rough calculations, and you get your chemistry book out, and you try and work out where these lines should be. You get some broad spectrum, and it's like there's lines here, and they're all kind of roughly where they expect to be. And then you do a proper calculation, and a miracle occurs. You realize that all of this light should be right here at 13.5 nanometers. And then you say, well, okay, but that's not enough of that light. And then you go, okay, well, maybe at 13.5 nanometers, plus or minus like, a few percent, like 1%. And you go, okay, well, maybe that's true for 10 plus, but surely it's not true for 11 plus. And you go and do that calculation, right, it's right there as well. What is going on? And so this idea that in tin, all of these lines are sitting right at 13.5 nanometers, and you have this really crazy process where you're producing all of these stuff, all these highly charged tin ions at all these different electronic states, and they're all producing light at 13.5 nanometers, and we do not know why. That's what I'm working on now. It's good. Another interesting thing you can do with atoms, nuclear fusion. You know about the ITER nuclear reactor, which is the big nuclear reactor that's happening. And one of the problems with having a big nuclear reactor that's, a conglomeration of many people countries has come together to put this nuclear reactor together, and they're making a diverter at the bottom of it, which is made out of tungsten. Probably know about this. It's tungsten in there. And what happens when tungsten gets into your reactor? Well, it quenches your plasma. Quenches means it radiates out all of the energy and basically stops it drops the temperature of your plasma a lot, kills your plasma. What we found out from fundamental atomic physics is that highly charged tungsten ions have a rate of recombination which is orders of magnitude, like 3 orders of magnitude higher than what was predicted because of something called quantum chaos. This is again another atomic property which is pretty unknown, or let's say not known by plasma physicists generally. And so when you have tungsten in your plasma, it's going to quench your plasma at 1,000 times the rate that they were predicting. What I don't know yet is how much that's going to destroy ITER's ability to function as a thermonuclear reactor, because we just haven't done that math yet. So that is another thing that we're working on. One of the exciting things that we're doing here is building our own tokamak. Atom craft is happening at the moment. It's being done over in the Faculty of Engineering, and physicists are getting involved with that as well. And one of the things that we're going to do, probably the second or third generation of atom craft, is actually be doing experiments on tungsten inside a working reactor, well, a working plasma anyway, and actually see what happens there. Cool. I have 3 minutes left. I'm going to tell you why atomic physics is hard. You know the Schrodinger equation. H psi equals E psi. Good. Solve it, you're done. We know this Hamiltonian for atomic physics. It is literally just the kinetic energy of the electrons plus the interactions between those electrons. I can write it down. You can all write it down. In fact, I've got 13 seconds. I'll write it down for you. H is the sum over all of the internal electrons. Momentum squared over 2 times that. That looks pretty good. Minus Z E squared over Ri. That looks like the interaction with the nucleus. That's good. And then I've got to sum over all of the pairs of electrons, a repulsive term, which is the repulsion between electrons. And that's all I need. That's the Schrodinger equation for an atom. Totally doable, totally solvable, right? The problem is, write down this wave function. What's this wave function here? I just care about the electrons. This wave function is a function of the positions of all of the electrons. Not so bad. R1, R2, R3, R4. How many electrons does tungsten have? Anyone?
At least 2.
N being big. I think it's 73 if I remember, 74, something like that. I can't remember. Right, N is large. So this is a function of like a lot of positions. Is that a problem? Yes, because it's not like these things are all separate. This is not a separable function. What happens is this actually has a dimensionality of 3n, which is bad. So if I remember that my atom is spherically symmetric, and then I do all of my angular algebra very carefully, and so I'm just left with one radial coordinate. And then for that radial coordinate, I want to represent on a computer, so I have like, let's say 100 points. And so I'm going to have a grid of 100 points. I think that's sweet. All I need is 100 to the power of n points.
It's not that.
And you think that's not so bad. So let's say that's what, 10 to the power of 2n. Cool. And n was what, 80 or something, right? 70. So this is 10 to the power of 160. How many atoms are there in the universe? 10 to the power of 80, roughly. And so even if each atom in the universe was representing one of our bits, we would not be able to store this function on a computer that was the entire universe. So we have a problem in terms of this calculation, and that is why atomic physics is hard. Cool. Hey.
Why does dimensionality become 3n?
Because of 3n? I wrote 2n here. That was 100 squared. But in general, if it was a three-dimensional problem, it's still 3n. Why? It's just because the dimensionality, because all of these degrees of freedom are related to each other in quantum mechanics. It's a Hilbert space, not just some multiplication of functions. Any more questions?
How would you derive like the energies of a atom that actually has electrons that isn't neutral, at least hydrogen?
Yeah, so how do we do this? We'd have to take, so for hydrogen, it's easy. Hydrogen, I don't have to worry about this guy.
How is it?
Totally solvable. We did it in third year. Helium, oof, problem. Okay, but once you get to tungsten, it's a real big problem. And the way we do this, of course, is by something called the single particle model. So the first thing we do is the original sin of atomic physics is that we write this thing down as I've got 2 s electrons in the one s shell, and then I've got the 2 electrons in the 2s shell. I've got 6 electrons in the 2p shell, right? Okay, cool. Yeah, that's great, but it's not true. Yeah, so then I have to make corrections to that. It's a first approximation because we can't do anything else, but it is the original sin of atomic physics. Where we need to correct it with relativity, and then we need to correct it with QED, and then we need to do, not QED like here, I mean quantum electrodynamics, a whole bunch of other things that we have to do in order to get this thing to be remotely accurate. How good is good? Currently, for a complicated case, we might get something like 0.1% or 1% accuracy in our calculations. That's not bad, but when you think about the experiment being accurate at 18 decimal places, it doesn't feel too good to be the dummy in the corner giving them 1% accuracy. Nonetheless, that's what we do. One of the things I'm quite excited about doing at the moment, I mean, I have written one of the best codes for doing these kinds of atomic physics problems called Ambit. But over the next couple of years, we're actually developing a completely new methodology, which will give us another, if not an order of magnitude, a factor of 3 or 4, hopefully. So that's the next thing I'm doing. I haven't told you that you can come work with me, but you can in principle. That's it.
Are there any prerequisites?
Yeah, be a genius. No. No, of course not. Everyone's like, I'm not that smart either. Like, I just good at computers because maths is hard.
Yeah.
Yeah. But there's different ways of skinning a cat, right? So no, there's, you know, if you're interested in stuff, you can do it. That's why you're here. Yeah.
Showing like branch fields, is that something a quantum computer computes?
This is wonderful. So one of the things that people who do quantum computers like to talk about is the no, this is not, why is my turns of phrase so weird to you? I don't know. But it's like one of the things is that you might hope to map a problem like this onto a quantum computer and then use that quantum computer to solve this problem, right? So actually the mapping from a quantum problem to another quantum problem, so essentially changing the Hilbert space from being around the atom to being distributed over qubits is something that people are interested in. I'm not quite sure that tells you anything more than just doing the experiment on the original Hilbert space, which is called experimental atomic physics. But it would be fun if you can do it. And maybe it would teach you something about the Schrodinger equation that is driving the physics of that system. But it's something that, like, that's an interesting idea. In the meantime, I work with regular old computers made with 13.5 nanometer light, made out of a tin plasma. It's crazy. Done?
Yeah.
I'm just wondering to what extent you use many body theory to figure out the Coulomb part.
Yeah, we use many body theory to work out. So once you get past the single particle model, you have to correct it. Then our physics starts looking a lot like many body solid state physics. And in particular, we use second quantization. We're using the tools of the field theory, same field theory tools that you'll be using in solid state physics or indeed in particle physics, but applied in a very different context. Yep. So again, we have like electron hole pairs, which will be like around the Fermi level. You've got like, virtual excitations and so on. And by summing these up in some sensible way, you can try and reproduce the entire Hilbert space. Yeah. Good.
Okay.
All right.
Thank you.
Awesome.
Okay, now just, 15-minute break roughly, just, get up, walk around, grab some food. There's a lot of fruit. Most of the good food's gone, so it's just fruit and fruit juice. Yeah, go for a walk around, ask questions to everyone, just have a chat. Right, so in the back.
So excited. Out when he starts. I had so much more hold on 1 second, and then he said,
Like,
that was hilarious, bro. Yeah, I know. Bro, it's so funny, though. I think he's so dirty.
or what, like another thing.
Yes is the answer.
That way, and then just share your screen.
Yes is the answer.
I almost
non-trivially. So,
Yeah, no worries. So I
they've solved these problems. You've got to do lots of operations. Right? So, the number of applications and contributions at the moment, you can do about about 500,000 calculations on time. By the time you get to 100 qubits, I kind of keep hundreds of plates spinning. The big game. Two-level system. Two-level system. Fine as long as it doesn't interact with the outside world. Isolate it.
But that, what is that? I have no idea. I just go the other side. You know what I did? No idea. No idea. No idea. No idea.
Useless. Do a knock operation or a land operation. Not interact with the outside. And you need it to interact. That's really hard. No, they're actually less than, except for special points which we call sweet spots. So, developed 18 months ago, showed that there are sweet spots, and if you get the whole thing, those characters, what they are about 1,000 faster. So, one of those. And then they're taking electron qubits and whole qubits, using one as memory and one as computation, like a GPU and a RAM. Right? So you take the electron spin qubit, which is very slow, you transfer the information, do the operation, and then transfer it back. So you can just put this. So that would be kind of one of the IBM, not actually Amazon is Microsoft and Google, they started showing Conaire correction. What that means is one qubit can get randomized by the environment. So what I'm going to do is I'm going to take this information. And I'm not allowed to copy quantum information. What I can do is I can store the information spread across 2 qubits, or spread across 3 qubits, spread across 5 qubits. And this is called basically the idea is you delocalize the information and you hope that if something messes this one up, it doesn't mess this one up, and then you can reconstruct it. Which is like a general. What I can do is I can just take this, if it's a 1 or 0, I take this, I copy it on 3. If one of them gets messed up, I just do a majority vote and say, well, you can't do that. If you look at it, you mess it up. So what you have to do is you have to look at 2 of them and say, I don't care what you're the same as this one. And if you're not the same as this one, reset it, but don't tell me what any of you are. So that's Conaire. Just like that. Error correction built in less fast. Yes. So with quantum information, you're not allowed to be redundant because there's no closed what you can do is you spread it across out into physical real space. That activates errors. And so spread it across 5 qubits, it's more resilient to errors. And if you spread it across 7 qubits, it's even more resilient to errors. So an engineer's approach is, well, let's just keep doing this. We just keep spreading more of the qubit out, more and more other qubits, and it will become perfectly resilient to errors.
Something to do with
The problem is that you need exponentially more qubits to make it resilient. So the physicist goes, well, let's look at the sort of members. Let's optimize them. If I can make a qubit exactly resilient to variables, it's by exponential the number of qubits we need to find. So there's still interesting now. I didn't think I would ever see this. That you can do Conaire Deagan. So to solve a problem like that, you're going to need, what did he say? 28, 300 qubits. So you'll need 300,000 qubits. Maybe 300,000 or 300 million physical qubits. So now you could say, well, how do I make 300,000 identical two levels of distance? Technology that we know has lots of things the same. Technology that's
Physics is better. I feel like that's gonna be the best.
we build millions of dollars. That's why we like to do it.
We only get
So yeah, your answer was, your question was really good. It's not clear if we can ever do this because no one's ever done it.
Maybe I'm
That's
not.
really
That's what
No way you said that. To be fair, that's what I feel like.
I wasn't sure what
slightly more
the polygon is not flat. One electron in two. He's got said we can count. And you know how many you've got. We have this sense, so we make one electron in.
You're doing like one
So if I've got one electron, that's artificial hydrogen. Two electrons in it. It's artificial helium, which is 3 electrons.
No, I mean like 50 or
So I can make artificial atoms. They just do it with 3 electrons. So I can do that. But what I can do is more interesting. I can now make so now I can take
It's like the same with the
But it's like, this is like half the.
yeah, no, the finals like
2 electrons. I bring them close together. There's artificial hydrogen. But actually, what I can do is make an array of about 1,000 atoms by 1,000 atoms, and that would define a source.
I have complex analysis.
Artificial solid.
We don't even
Determines only the structure. Same atoms. One of them is one of them is so by changing the arrangement, atoms change diamond is graphite changes electrons. Graphite is superconductor, diamond is not. So if you make artificial matter, you can change the arrangement of atoms. Say, well, maybe I want to get a square array. Or I want to make you. Why do we care about this?
And then I have the pushback.
Do we know how they work? Any theory that describes how matters discovered in the 1980s. So
That quantum and that's
what about you? Ceramic material super. What if they stole it? No idea why. What if he stole it? They don't even know what kind of super. It's massive. Yeah, because like it's such an big. We know exactly what it would be the crystal structure. We know the elements.
guys, can we
know how
that's the they're all waiting outside actually. Yeah, do you have the confetti room?
Yeah. See,
that's my question.
because as soon as you've got
got. It's like atoms.
Yeah, that's.
Problem solved.
Yeah,
I don't know.
I don't know where to go.
Do we make an artificial mimic that they said that we need measuring temperatures?
Don't be afraid.
But then we can do things that how do you do with real age? Probably like
It'd be like a quantum mechanic that they change the information. They'll show you the number of electrons on one of.
You
Start doing experiments.
Yeah.
I mean, if it's not real, we're actually behind. So I think
What do you guys all think? You're somewhere past that. Be like just
like doing that.
so you use your race police and it's just not.
That's so good. It's much better to feel very like just just figure out
Then the other 25% is all exams.
Becoming more.
oh yeah, and then 85% and then the engineers. Yeah, so like, oh yeah, I was like, you should go and get other it's like how it's like how the original they don't really get no they just come in like oh this week
Oh no.
oh my god I know exactly
pressure. Not even vibrations.
Yeah, no, that's okay. I think yeah, more guys feel like that right? That is mine. That is mine. So I think I'm just like.
Oh wow, and there's no, my thinking. You work out at BCS.
Say that.
Righteous minds arguing.
Okay, yeah, I mean, it's
My theory. No, it's mine.
Yeah. I think you can
You would take these high temperature superconductors.
Makes sense. Like then we have a
I have three physics majors.
I forgot about
No, I've heard of it. And then when he said, yeah,
I just remember it. You have some sort of license.
Yeah.
Which is fine, but you want to know about price first.
I don't know, I mean, I should. Like, people need to do it. I didn't mind. I didn't like them. I didn't like the question for bigger.
Space gross.
I know. You guys like it more than Luke system. This is so rich. I think I would like business. Yeah.
Yes.
I haven't had
Schmidt are really good thing. And you can just in terms of hearing, right? You don't
particles from here are just falling down to the low energy level, but it's actually not what's going on. Oh, I think we can dispense with that, but that was, the other is a picture of the current, but since time is going on, I think I should. Yeah, this is what happens to the current computed for that model. As you would expect. So at the beginning, the current is injected and it goes every which way because it frankly doesn't care where it goes. It has to get out of the way because it's being pushed up. So it goes that way and it goes that way, and that's why the current on that side is negative. As time goes on, the left and right sides even out, what you get is current in the intervening interval. So all the current that came in is now all going out again. But that's actually a minor point. The important point was the first example. All right. So moving really. Yeah. Okay. We'll dispense with it. Oh. Here's essentially the conceptual picture of this little model I just ran the video for. You have a pump, and obviously it could be a little old man, turning the pump, or it could be a windmill connected to the impeller. And what's happening is some external energy source is pushing stuff in and sucking it out at the same time. You can think of a battery as essentially doing that. Somebody is turning the handle. It's obviously the internal energy you've stored up to charge the battery. And that is what is driving the electrons around and around and around. The important thing about the process is that it's actually non-conservative in the sense that Poisson's equation gives you a unique potential for your unique charge distribution. But these EMFs are not like that because they're not driven by the Poisson equation, so they're not conservative potentials. Right? Every time you go around the loop, you've lost energy through Joule heating, so it has to be supplied to you again. And therefore, dissipation is the other part of the process. Now, what is the difference? If I have a simple circuit, now I'm going to always talk about injection and removal of charge, right? So this is a current generator. What's the difference between a macroscopic device and a microscopic device? Tens of nanoscales, fractions of microns down to nanometers. Well, the difference is that in a metal, the distance it takes to neutralize a small charge, if you put in a small charge, or conversely, if you extract an electron, you're going to upset the local distribution of particles, of charges, and the screening length essentially tells you what kind of sphere of influence is around the impurity. Well, in a metal, this can be very short. At least a nanometer. I think it's probably less than that. Memory fails me, but it's extremely short in a good metal like aluminium or silver. All right. The trouble with, see, if you have something like this, where the screening length is insignificant in comparison with the size of your device, you can think of the device as kind of semi-independent of the circuit. So you can string devices, and that's why, you can add resistances together linearly, because the distance between one object and the next device is much larger than the screening length. In this situation, you don't have that because the screening length is about the size of the so-called device. So the problem in modeling these things is that you basically need to account for the whole thing. And if you need to account for the whole thing, it's very important what kind of boundary conditions you put on the problem. So if I have a nanotube, what I want to do is have very good ohmic connections, and very good ohmic connections are strongly metallic. So outside the circuit, you don't need to worry about the physics anymore, because essentially, you know, a certain amount of current goes through. There's almost no potential drop here because the charge distribution is uniform almost everywhere, except around the neighborhood of the connections and in the device itself. All right, so okay, let me go quickly to some results. This is a beautiful result from an epitaxially grown quantum wire, almost one-dimensional. And if you plot the conductance of this wire as a function of the number of electrons that you can modulate the number of electrons in the wire through a gate, as we've heard before. Okay, so what you get is very good, very flat plateaus where the conductance is constant and almost a multiple of the fundamental conductance, which is called the Landauer quantum, it corresponds to something like 13 kilo ohms if you calculate its resistance, its inverse. The conductance is generally given by the fundamental quantum times a transmission probability, which obviously shouldn't be bigger than 1, right? So let me show you. I'm going to skip that. I'm not going to talk very much about the techniques that we use, but let me show you that the conductance, the quantum conductance can actually exceed unity, which is not supposed to happen, okay? This is an experiment from 2004 on the same, I think, the same beautifully clean wire that we had in the first example. Right. You can see that at 0 voltage, it's very, very high quality, very close to the ideal of unity, but not quite. Now I put 1 volt across the device, which is, I forget exactly how long, but it was nearly microns long, this wire. And the conductance at 1 volt of potential difference just happens to hit the ideal. But it doesn't stop there. If I double the voltage, I now have a conductance which is still very flat, but bigger than 1. So how can that happen? And you go on, okay? So this is data. Well, the experimenters didn't do the calculation because I don't think they knew how to. And you cannot do this calculation using the lemming model where electrons just drop off a cliff. That does not, there's no way you can handle this kind of effect. They did suggest that it must be some interaction between the lowest band, and here is where the first conduction band starts. And here you get another jump in the conductance. There it is in the theoretical model. That's where the next higher level in this quantized wire starts and contributes to the conductance. So they speculated that what was happening is that there is some crosstalk between this band and the next band. And in fact, this is how this calculation is based. It's actually quite a messy calculation. Even if you're doing one-dimensional physics, the mathematics is apparently quite simple, but this is actually a highly self-consistent calculations. You cannot solve it analytically. You actually have to do it on a computer. But you can see our model is too simple to actually quantitatively follow the experiment, but we do get a plateau. And the reason we exaggerate the effect is basically because we haven't really got a good model for the inelastic scattering that's happening in this model. And since then, I haven't actually gone back to try and improve the result because there's no point in the sense that I could do, what's the word for it? I could twiddle knobs and put in some kind of adjustable parameter to make it fit, but that's not the point. The point is that the conductance does exceed the bound that it's supposed to satisfy. And there is a mechanism, even though it doesn't match the experiment very well, there is at least a mechanism to show that the enhancement does happen. I think that's probably time enough. I'm not going to discuss, this is a totally different calculation about the fluctuations in the electron current when the system is driven by a very high internal field. But I won't go into that. What are my parting thoughts? Well, the real take-home message that I'm giving is that a working circuit is always electrically closed. And if the working circuit is always electrically closed, it doesn't actually make sense to talk about higher levels and lower levels because you're in a closed loop. Because of the boundary conditions of a circuit, you have to take into account the strongly metallic leads that connect to your device, because it's the strongly metallic boundary leads that actually enforce the neutrality of your structure and stabilize the chemical potential. So left and right doesn't matter. The chemical potential is always measured from the bottom of the conduction band. And when you apply a voltage to something, you lift the whole thing bodily, okay? You don't change the chemical potential because it's global. Okay, thank you for that.
Thank you very much. I don't have any questions. Hopefully, I guess Instagram, everyone's all happy to chat. Okay, I think I just have to get the text sorted, but yeah, thank you. Good.
Thanks, David.
Oh, good. Here we go now. Okay, now give it up for Michael Schmidt.
Okay, good. Hello, everyone. So I will talk a little bit what we are doing in theoretical particle physics. I will talk about what I'm doing. There are also other people working on kind of theoretical particle physics. There is Deepan Singh Gupta, Yvonne Wong, and then Ian Harman is more working on cosmology, but yeah, it's all kind of cosmos/particle physics. Actually, no, that doesn't work. Good. Is there any new physics beyond the standard model? Any? You think so? Yes or no?
No. Maybe what?
Yeah, yes, maybe no. No? Okay, good. So let me give you a few arguments why there should be, or why we know there is. But maybe I should also briefly say what's the standard model, because I see there are many who are in first year. So let me briefly explain. So here on the right-hand side, you see basically the particle content of the standard model. So these are all particles which are there. So we distinguish between the so-called fermions, or the matter fields, which basically make up all the matter we know. Specifically, the left column here, see the up quark and down quark, they make up protons and neutrons. Then we have the electron, and the partner of the electron is the electron neutrino. There are 3 copies of that. So basically, that's the so-called first generation, second generation, and third generation. There is no clear idea why we have 3 generations as such. Maybe one reason why it's good to have 3 generations, because without 3 generations, we don't have CP violation. CP violation is necessary to generate matter-antimatter asymmetry of the universe. So basically to generate more matter dynamically. The second part here is the forces. There are gluons, which mediate a strong force, photons, which mediate electromagnetism, and W and Z, which mediate the weak force, which is, for example, responsible for beta decay.
And finally, the Higgs boson up here, which is important to give mass to actually all the other particles. So why I said that there should be new physics beyond the standard model. So we have several observations which can only be explained with new physics, cannot be explained within the standard model. So one is neutrino masses. So neutrinos have been thought to be massless, and in the standard model, they're exactly massless, but we have observed 20 years ago, a little bit more, 25 now, I think, 1998, we observed that neutrinos have masses because neutrinos oscillate, go from one flavor to another flavor. The muon neutrino goes to an electron neutrino. We know that there should be some matter, some more matter in the universe. Julian mentioned that, and there is also, we know that there is much more matter in the universe than antimatter. And all of that needs some explanation which is beyond the standard model. And there are a few other unexplained anomalies, and I will talk about one of them later. But those are probably, so that one is really confirmed, everything. There has to be something, and we know it's there. So for the anomalies, that's still more uncertain. There are some hints, some evidences, but it's not guaranteed to be there. So there are also some theoretical concerns. So for example, in the standard model, you see I didn't put a graviton there. I didn't include gravity. So that's a theoretical question. I already mentioned why should there be 3 generations of the standard model. Any explanation of the masses, I don't think you can read the numbers which are there. But if you could read them, you would see that the top is much heavier than the charm, then much heavier than the up. And similarly, the bottom is much heavier than the strange, much heavier than the down. So the 3rd generation is generically much heavier than the 2nd and much heavier than the 1st one. And so we don't have a theoretical explanation for it. We also observe parity violation. So you would think that if I mirror it at the origin, the universe, if I mirror it at the origin, it should be invariant under that, but it's not. And one reason why it's not is because of those weak interactions of those W bosons. They break parity and also break CP. So CP is the combined, you change all particles to antiparticles, and at the same time you mirror it at the origin. That's a CP transformation. So there is no explanation for it. And then there's another thing, a problem, which I just mentioned in passing, is we observe CP violation in weak interactions. So in interactions of the W boson specifically, but we don't observe any CP violation in strong interactions, so which are mediated by the gluons, even though I could add a term to the Lagrangian, which I could write down. And so there is there are many explanations, but there is no confirmed explanation. Let me put it that way. There are many theories. Okay, what I should say is feel free to ask questions and stop me. I will just talk. So what I want to talk about is what is called flavor physics, and that deals with those 3 generations, that there are 3 copies of it. And so one specific class of processes which helps us to understand better the standard model, or what may be beyond, is to look at processes which are very rare in the standard model. Because if the process is very rare in the standard model, then the new physics contribution can be very small, and I can still see it. So it's very sensitive to any small deviation. And so there's a specific class of rare processes, which I want to briefly argue. Okay, that's probably too technical. So so the Z boson couples only in a flavor diagonal way. So the Z boson couples only to the same particle, actually. So Z boson couples a top with an anti-top, but it doesn't couple a top to a charm. And so what that means, and similarly, the Higgs also doesn't do that. So in the standard model, if I just write down the Lagrangian and look at the interactions, I see no transitions which go from the top to the charm, So transitions which don't change the electric charge. However, since the W boson will mediate those, and they will mediate those at a higher order effect when I do the expansion. So therefore, those processes are suppressed and they are rare. So those processes which, for example, here change, if you look at that process, there is an anti-down in a strange quark, and they annihilate and couple there to the Z boson technically. And this process is rare. It's very rare. And the other reason why I want to look at those rare meson decays is because I can produce them. I can produce a lot of them. So what I do is I have an E plus, E minus beam. I collide them onto each other. I collide them at a resonance where I produce an upsilon 4s. Upsilon 4s decays dominantly in B plus, B minus. And then I produce basically those B mesons. And I need many if I want to look for rare processes. I have to basically need large statistics. And there are also other decays one can look at, kaons and so on. And one reason to look at kaons and B mesons is they are easy to calculate. So D mesons are much harder to calculate because there's no small quantity I can expand in. So the specific process I want to briefly talk about is where B meson goes to kaon and nothing else, basically just missing energy. So a B meson contains a B quark, or actually more precisely an anti-B, and the kaon contains a strange interstrange quark. And those processes are suppressed, and in the standard model, they are produced via those two diagrams. And the nice feature about them is, so two nice features. So one is it's very easy to calculate. I mean, easy to calculate, there are no difficult corrections. So there are no basically interactions which connect the strange quark, for example, to the neutrino. So everything is basically, I can cut the diagram here and can treat the leptons, the neutrinos, separately from the hadrons, from the hadronic part. And that's is very good because it makes, I can make it a much more precise calculation. So typically the hadronic part is difficult to calculate. And secondly, it's sensitive to both anything new here in the loop, so heavy particles, and it's also sensitive to something light, which is being produced. So I said here B2K invisible, I don't know what it is. So in the standard models, it's neutrinos, but it could also be some new particles, which are light and which are very weakly interacting with the standard model. So the only thing what I know is when they're produced, they escape the detector and I don't see them. And so what's interesting is, so Bell 2 is expected to measure all of those processes at the with about 10% precision. So there is 4 different channels one can look at, and they recently measured one of them, the first one of them. And so that's their result. And so what you can see here is in black is the data. There are some backgrounds in those different colors. So that's what, so I should actually add here. So that's basically number of events in a certain bin, and they bin it in some variable. That's kind of technically the energy which is carried away by by those neutrinos, or the 4 momentum squared invariant mass. So they cannot exactly reconstruct the 4 momentum. That's the quantity they measure. So what you can see here, there's first of all in red, that's the fit, assuming kind of the standard model signal shape of that to that data. So basically, there's a standard model calculation for B plus to K plus nu bar, and you can perform a fit. And I unfortunately didn't put a number there for the result. So the standard model prediction is roughly 0.5 times 10 to minus 5. The measured value is 2.3 times 10 to minus 5. So that's roughly a factor of 5 larger. And also the other point is that you see here that it doesn't fit the data very well, but because there is a slight excess at 3 to 5 GeV squared. So that's one hint of what could be new physics. But of course, it could also be that's the first measurement. We have to wait for more data and see how it develops. So Bell 2 took so far less than 1% of the data, which they will take. But in any case, it's interesting to look at those processes because it will give us a new window to look at new physics. And I want to talk about one specific scenario which could lead to that. So I should look basically here. That's some other theorists did that fit. And to look at the yellow curve, they see that provides actually a relatively good fit. And that's basically a 2-body decay. So the idea is you have a B meson decaying to kaon plus 1 other particle, instead of basically 2 neutrinos into 1 other particle. And so that one other particle has a mass of 2 GeV. Okay. So let me look at that one scenario. So that particle could be a scalar particle. So the idea is you introduce a new particle which couples to all the other fermions in the standard model exactly in the same way as the Higgs does, the Higgs boson, but its couplings are suppressed by a so-called mixing angle. So they're suppressed by a factor of 10 to the minus 2, 10 to the minus 3, and are just, that's why we haven't seen it yet, because it's so weakly coupled. And if that particle would be at 2 GeV, which is here, there is the current, sorry, I should say there are 2 parameters in the model, the mixing angle and the scalar mass, the mass of the particle. And everything is fixed in terms of those 2 parameters. I should maybe add that model, it's easy to write down, it's well motivated, it's UV complete, there is nothing, it's extremely simple. Okay, but there's a problem with it. And the problem are their constraints, because all the parameters are fixed. So we also know how the particle decays, for example, in muons, and muons are easy to see in a detector. And so there's an experiment at the Large Hadron Collider, it's called LHCb, and that basically produces many B mesons. And what they look for is they look for a B meson decaying into that kaon plus a scalar. So the scalar they don't see, but then they look for a displaced vertex away from the interaction point where the protons collide. They look for a displaced vertex where suddenly 2 muons appear. And they haven't seen anything, and they put a constraint, and that's basically this constraint, that line here. So how do you get around that possibility, around that bound? You have to introduce an additional coupling of that scalar to something which is invisible. That could be sterile neutrinos, something like a neutrino, or dark matter. So that's what one can do. So we looked at it, we wrote down a model as well. And so then one can think about how do you see it then in Bell 2? Or back then when we looked at it, there was no Bell 2 yet, no Bell 2 analysis. We looked at Barbar, which did something similar. And so here you see again that Q-squared distribution, and you see how the signal would look like in the data. And then you can constrain, then you can basically look at that parameter range. So kind of sine theta was the mixing angle, and the invisible decay width is basically that additional coupling. And you see that LHCb puts those, the constraints from LHCb are those dashed lines. So maybe just look at the orange one, and the constraints from Barbar are the solid line. And so the one which would correspond roughly to the observation which we have is this dot dashed line here. So what we need is we need some invisible width of roughly milli-electron volt or larger. And that's then consistent with what's observed. So technically what we are doing is we're looking at theory explanations of what experimentalists measure and make then predictions where you could look for something for other experiments. Yeah. And so just to give some other example, I did that was from honors project of Felix from last year. So we looked at, so there's an experiment at CERN that's called Phaser. You probably haven't heard about that. So the idea is very simple. So you have the Atlas detector, you have 2 protons collide, and you place another detector 480 meters away. So I should actually maybe just draw a line. So you have here Atlas detector here. You put your other detector over there. So most of the particles which are produced at the LHC are going actually along the beam pipe. Most of it is basically going in this direction, and only very few is basically going in this direction. So Atlas is only looking for those which go in that direction, and here we have ones which go along the beam pipe. So the second detector, there's about 100 meters or 150 meters of rock in between that will absorb all standard model particles, apart from neutrinos. and a few muons. And then you can look for any other signal which shows up in the detector. And that could be any new light particle which is produced there and which is weakly interacting and long-lived and can reach the second detector. And that's basically what we looked at here. So we produce something what is called an axion-like particle. An axion-like particle, they are naturally light because they are emerged from, if you break global symmetry spontaneously. So if the theory is symmetric under certain symmetry, like if you want symmetry, phase redefinitions, but the ground state is not. So that's spontaneous symmetry breaking. And there's a prediction that for every time you have a spontaneously broken global symmetry, you get a massless or almost massless particle. Yeah?
If a collision creates a non-standard model particle that doesn't interact much, wouldn't that just be detected as a difference in energy by the original detector? Why do you need another detector?
Okay. So Atlas is not instrumenting anything in that direction. That's going along the beam.
Oh, it's only instrumenting for like stuff.
Yeah, it's only basically instrumenting in the away from it transverse. So we are looking really at something which is going far forward. And yeah, good question. But you could do that in principle. So what we basically looked at those axion-like particles and how they what you can see in 3 different types of detectors. So Phaser and SLD at LHC are operating. They have been built recently. That's quite cheap detectors. And that's Phaser 2, which is an upgrade. And what you can see here, existing constraints in gray, and we calculated in those contours, or Felix did, I think. Should say he calculated those contours. And for that, you have to simulate how many you produce, how many axion-like particles, and then how they decay in what's their lifetime. And we can do the same thing for other particles as well. That's basically vector boson, a new force carrier, which one could imagine. But I think I should wrap up. So let me just say we look at different things. So the idea is really to look at phenomenology and to think about what kind of models could explain it, and then also to test it, make predictions which can be tested. And maybe just one thing to highlight, which I'm at the moment excited about, apart from the flavor physics, is infrared divergences and scattering amplitudes. That's something, it's more theoretical problem because, so if you look at scattering amplitudes, they are, and if you don't sum it up correctly, so that you have to write down Feynman diagrams. So each of those terms corresponds to a term in your matrix element. And you have to add them all up. And when you add all up, the divergences should all cancel. Physical result should be finite. However, if you basically would only look at the loop corrections, you see that there's a divergence. And if you only look at the real emission of an additional particle, you see a divergence. So there's a theorem at 0 temperature, which guarantees that all divergences cancel, but there is none at finite temperature. And so we want to look at finite temperature, what happens, because that's relevant in the early universe when you have, for example, dark matter annihilating, and there are scenarios where you can get those divergences. And what people so far did is just including other effects, which basically cut away the divergence, but not and it exactly cancels at a fixed order in perturbation theory. Yeah, so thanks a lot. I'm happy to answer any questions. We'll move on, right?
Yeah.
Move on.
Yeah, thank you. Yeah, people can ask questions after. If Mikhail doesn't run off. Thank you guys so much for sticking around. We got one more talk from Conaire. Trying not to keep you around too long. There we go. Okay, sweet. Get on, Conaire.
I don't know who Conaire is, but my name is Conaire. Maybe the best for last. So I'm going to be talking to you about my work that I do. And I've also got a challenge for you guys at the end. You don't have to do it, but I really want you to do it. So pay attention to that. So I study the surface of stars, and I came up with a really dumb title here. But basically what I study is I study sunspots, which are these things here. And just for scale, that's Jupiter. So these are structures on the sun that can go up to the size of Jupiter. And they're just dark spots. They're where the magnetic field comes out of the sun. Anyway.
That doesn't work.
So you might be okay. Who cares about the surface of the sun? Well, I do, and hopefully you guys will. But also people who look for exoplanets, the host star of exoplanets is basically where all the noise comes from. So if you want to get down to smaller and smaller exoplanets and more interesting ones, you need to know your star very well. And also if you study the sun, it's also quite important. So I don't know what level of amount of solar physics you guys have taken, but sunspots kind of appear in these kind of bands on the sun where they only appear a little bit above the equator and a little bit below the equator. And that where those bands are changes with time, and it's related to the solar cycle and also like the magnetic field of the sun, which we don't really know much about. So that is important to know about, especially because we live here. That's the sun. The sun, coronal mass ejections, which are the stuff that cause auroras and stuff, basically come from sunspots, and we don't really know how these work that well. And this could maybe destroy all technology one day, which is not good. Probably won't happen, but important to know about. So what does the sun look like? You should go outside and look up, but currently it's nighttime, so here's a picture. This is what it kind of looks like in H alpha, and it's probably what you guys think of the sun, with like this big flaming ball of flames. This is quite noisy. In most wavelengths of light, it looks something more like this on the right, which is like a quiet sun wavelength. And you can see on the right-hand side, the only structures you see are these dark sunspots. So when people design missions to look for exoplanets, they choose the wavelengths to avoid all this noisy side, and they choose something that looks like this, but there are still these sunspots. Okay, so that's what the sun looks like, and the sun is really close and we can see it. What do stars look like? So this is a video I took last weekend when I was observing, and this is what the big telescope out in Conaire sees. Stars are just basically point sources of light. You can't actually resolve these stars. So if you can't resolve a star, how do you learn anything about the surface? Technically, for a couple stars, you can resolve them. There's Betelgeuse and then there's Antares. You only get a couple pixels here. You're not really going to be looking at the stars and seeing what is going on. So how do you resolve stars? How do you learn about the surface? There's a couple ways. One of the ways is just go there. This is really not going to happen. Breakthrough is trying, but they've basically given up. They want to send a spaceship to a different star. It's not going to happen. So that's out of the picture. Another method is called light curve inversion. And I have opinions about this. And then there's a third thing that I'll get back to. So light curve inversion is something like this. So on the left-hand side, we've got the surface of the star. You've got some dark star spots rotating across it. And as you track the brightness of the star over time, you get a light curve. So we go, okay, well, this will generate that. Maybe we can go backwards and generate this. And do you guys think this would work? Hands up if you think that would work. Okay, well, a lot of people think it'll work. It doesn't work. Well, kind of works, but it's very degenerate. That means there's a lot of solutions that'll give you exactly the same light curve. You can see here, we've got a two-dimensional surface and a one-dimensional signal. You're losing information. And there was this paper a couple of years ago from Liles, and they were looking at light curve inversions. So what we have here is we've got 6 different stars, and this is just at different rotations. So each row is a single star, and each of these stars has 1 spot, 2 spots, 3 spots, 4 spots, 5 spots. And then this is a light curve for all of them. So they've got different surfaces, exactly the same light curve, which is not good if you care about looking at the surface of stars, because you just don't know. And I'll just take a quick aside here. I'm going to talk about spherical harmonics. They're useful for stuff. But if you think about like a point in 3D space, you can map any point in 3D space by using a combination of x, y, and z vectors. These are called basis functions. If you've done a bit of mathematics, you might know about them. Spherical harmonics are kind of similar to basis functions, where you can create any map on the surface of a sphere by using some combination of these spherical harmonics. And there's an infinite amount of these, so they're a little bit different. But you can see here, if you use more and more spherical harmonics, you get more and more accurate pictures. So this is a way that we can kind of measure how much information we can recover. How many spherical harmonics can we get? Kind of correlates to how much information about the surface we can get. Okay. So if you do some mathematics, you'll kind of work out that light curves can only give you 25% of the information of the surface, which is why there's so much degeneracy. We can only get 1 in 4 bits of information, which is not good. So what about other ways of learning about the surface of the star? Can't go there. Light curve inversion is not really that good. Also, I should say, every single possible light curve can be generated by 2 spots on a star. Every single possible light curve. So that's not realistic. So there's another thing called astrometry. Does anyone know what astrometry is? Not astronomy. They're very similar words. It's basically just measuring the very precise position of a star relative to other stars. So we got these background stars that we're just going to pretend aren't moving. Astrometry is measuring exactly where this middle star is in relation to that, just like an RA and DEC, basically X and Y position on the sky. If you're searching for exoplanets, one way to do that is by looking at how much that position changes as the planet goes around and tugs on it. And that's what a lot of astrometric missions are doing. None of them exist at the moment, but they're going to be funded. But there's also the noise from the star, which basically you got the planet that pulls in the star, but you also, the star kind of just moves around by itself, or appears to move around because the surface is changing brightness. A star just looks like a single point source of light. So when the surface is changing, that point source of light kind of looks like it's wobbling. And you might confuse that for an exoplanet. So if you want to find exoplanets using this method, you need to know the star. So there's a couple of missions that are being proposed, or being funded actually, to use this astrometry to find exoplanets. One of them is Tolman. This is based out of UCID. I'm on the science team of it. Got a very long acronym. The reason it's got that acronym is Tolman is the name of Alpha Centauri in Arabic, just kind of fixing it. This is like a $1 million budget telescope, space telescope. Not going, probably not going to work. Anyway, but NASA has their own version that used to be Tolman, so it kind of branched off. There's drama there, but they've got a $150 million budget, and they've got a telescope called She-Ra, which this is She-Ra from the 80s. You guys are probably too young. I'm also too young for it. But this, so we got some telescopes that are being funded that are going to get launched into space that will use astrometry to try and find exoplanets. And the reason why I care about astrometry is that you can use astrometry to learn about the surface of the star. We got the same GIF as before, where you got the spots kind of rotating around, and it generates a photometric signal, a light curve. But it also generates an astrometric signal, which you can kind of think of as like the center of mass of all the light. So you can see as the star rotates around, right now it's solid, so it's staying right in the middle. It's going to get deflected a bit by the dark spots, and then this big dark spot is going to change the apparent center of light from the star. And this gives you a lot more information. It's a 2D signal. When you're measuring this, you also get a 1D light curve because you just got a camera basically. So you got way more information. So, for example, is a way that this can break some of the degeneracies. So we've got 2 different surfaces here. One on the left is just a single spot. Here, there's a kind of couple other spots here. They've got identical light curves there. You can see that, but they've got different astrometric signals. So we've just broken that degeneracy. We know more about the surface of the star. But how much more? Well, what I've done here is I've colored in all of the spherical harmonics that you can get from photometry. So the gray ones are the ones that you can't. The colored ones are the spherical harmonics that you can get from photometry. So this is photometry, and this is astrometry. So you can see, you get way more, 25% for photometry, and you get about 50% from astrometry. Not perfect information, but way better. But you can also combine astrometry with photometry, and you get about 70. So now you're getting the bulk of the kind of spherical harmonics. You're getting the bulk of the information about the surface of the star. So let's kind of see how this works in real life. On the left here, behind this mysterious box, I've got the true surface of the star. And on the right is the recreation of the star from the information that we can get from photometry. Does this look like anything to you guys? Just yes or no? Just a whole bunch of messy, splotchy stuff. That it's not meant to be like that. Let's look at what information we can recover with astrometry by itself. Now, these are starting to look like letters, right? So it might be hard to actually see what it says. A lot of these are upside down. You might start to see, looks like it says fart. It doesn't say fart. But if we add photometry back in, so right now we're at 50% information. If we go to like 70% information, we get something that looks like this, and it's going to repeat the message soon. That is meant to be something, but I don't know. But theoretically, if a whole bunch of really intelligent aliens could modify the star to write messages with dark spots, they could say greetings, Earthlings. If they wanted to. That's not really possible, but you know, if the star looked like this, we could recover this information. And going back, if we're through light curve stuff, this is what people say they can learn about the surface of stars. Crap. You get much more information. And just as a comparison, this is photometry, astrometry, photometry, and astrometry, and this is the ground truth. So we don't get the full information, like you probably didn't pick up on that little alien guy there, but we're getting so much more information. And the idea behind this is in real life, obviously the surface of stars don't look like this, but we could learn about like the distribution of star spots and do that act the same as star spots on our sun. We don't know. Our sun is very different from other stars, even stars that are very similar to the sun. Our sun is way less active than them, which is probably why we exist. But like, yeah, we don't know much about other stars. If we eventually want to try and find Earth-like planets or even be really out there, go and colonize those planets, we need to know about those stars. We don't know much about those stars. One way we can learn about these stars is to learn about the surface of the stars, learn about like differential rotation, the dynamos of the stars, how they work. And one way that you could do this is with high precision astrometry. So to summarize, there's new telescopes that are being built. And maybe when you guys are in grad school or whatever, these telescopes might start to be getting data and you could work with this data. And they will allow us to study the surface of the stars. So that's my talk, right at 9 o'clock. But the other thing I have is these little business cards here. It's not a business. I don't do business. I teach it, but I don't do it. Anyway, there is a message on these cards, something, and I want you guys to try and decode it if you want to. There is a prize. The prize is either a beer or coffee. I'm not made of money. But on the back, there's a digital copy of the numbers, so you don't have to like transcribe it. And then there's a post-challenge survey. This is something I'm doing because I want to write maybe a letter, like it's like a mini article, like a mini paper, or like a blog post or something. So I'm quite interested about how people approach this problem and what it means for something. And if I tell you what that something is, it's going to spoil the problem. So I'm kind of being a bit cryptic here. But I will say this, you don't need to know cryptography to break this. You can do it with a pen and paper, although a computer will probably help. There's no red herrings. I just want to see if you guys can solve it. There's a whole bunch of them just over there. If you would like, please take one. I'm interested in hearing your responses. And again, there's prizes. So thank you.
Any questions?
Any questions?
Thank you. Thank you again. Thank you. Thank you everyone for coming. It is late, so you get to bed. Thank you for those who sticked around, and hopefully we see you at some future events. Physoc. Thank you. Thanks, baby.
Yeah, that was like, I remember the day, like it took 3 hours.
It was good. Pretty much everything was without being
Allocate one.
I'm doing a video. Yeah, I know. Yeah.
Okay.
Thank you.
It's reading, so.
With this answer, you can like obviously.
No, right. No, it wouldn't surprise me. I probably could. I mean, either one.
I'm recording.
Yeah, I can.
Like I'm staring at it. Okay.
The truth is that this is meant to be a small
My eyes started like blurring out.
Oh.